All right, good morning. So I want to tell you today about some experiments that we've done, and I'll give you evidence that at least in the experiments we are using green fluorescent protein. These are large molecules. There are fluorophores in them, and then show that they are capable of creating entangled photon pairs. What do they tell us about entanglement within the molecules? Again, that's a question that remains to be investigated. And also whether if this GFP was expressed in live bacteria or live organisms, I think that we will not see any change in the experiment, at least the way I will describe them. So what consequence they have in terms of our understanding of the bacteria itself, or how these proteins behave in terms of their entanglement or any of the quantum properties, I think that's an open question. Again, our experiments are done at the time scale of a few hundred femtoseconds, so one can view them in the sense of a very short time scale and understand them that these coherences at least persist that lead to the entanglement properties on the photon pairs. So without further ado, let me, okay, I guess I need to. All right. So you heard a lot about quantum biology and many of these different systems that have been talked about yesterday. And my background is in the context of quantum optics. Career made with doing experiments in inanimate systems, not non-biological systems, using processes like spontaneous parametric down conversion or spontaneous full web mixing, and use them to create entanglement in various systems for sensing applications, for quantum communication applications, or similar quantum technologies. So a few years ago, we started asking, why not use a system that's biologically relevant to do similar experiments? And we decided to use green fluorescent proteins, and our motivation, in a way, can be summed up in these points that I've made here. Fluorescent proteins, they are naturally occurring, but they were genetically engineered to create variants with fluorescence properties at various portions of the electromagnetic spectrum. And then, of course, they have internally very high fluorescence efficiency. That means that they interact very strongly with electromagnetic radiation. And they resist decoherence, and I'm very loosely using the word decoherence here for now, that the fluorophore is very protected. So if I take these proteins and put them in some kind of a solution, the fluorophore of an aggregate concentration of these proteins acts as if these are individual molecules that do not interact with each other. If the concentration, of course, very, very high, then certainly quenching type of effects start coming in. And then more importantly, these are genetically engineerable, as I said, from the naturally occurring GFP, various different cell lines or the different variations of these proteins were created, and they can be expressed in live systems. So then, is it possible to optimize some physical characteristic that has some quantum heuristics, such as entanglement? So can I engineer a protein structure that optimizes some quantum feature in some way? I mean, that's the central question that motivated us. And then the first question was, what quantum attribute? And that's the experiment that I'm going to try to describe to you. And of course, once we have that, there is potential for using applications going into live systems and expressing these proteins in other kinds of bacterial cell lines and so forth, and then probing them in some quantum mechanical setting. So that's sort of the motivation. So here's, I'm going to give you 20 minutes, not long enough, so I may go a little bit fast. How we started to probe the nonlinearity that these proteins have, and a particular kind of GFP that enhanced GFP that we use. We measure the amount of nonlinearity it provides under optical excitation. And then we undertake four-way mixing utilizing this nonlinearity. And once you have that, you have quantified the kind of nonlinear interaction one can have, then it permits us to create photon pairs that show entanglement properties between them as these pump pulses create excitations in these GFP molecules contained. And of course, we compare that with other kinds of dyes to make sure why is GFP relevant and why not any other dye molecules, for example, in some solution. And we compare and we generate photon pairs, and I'll show you why GFP is better. Again, the conjecture is that it is better because these fluorophores in GFP are kind of protected by the beta barrel structure that the protein has. And then how that can be translated into actually entanglement on these photon pairs that are emitted. And we measure those photon pairs, and what do they tell us about the molecular structure of the protein. And again, that's indirect evidence, that's not direct evidence. And I will conclude and take some questions on that. So, and again, this is our way to create entanglement. I'll come back to this. So let me start by just probing the nonlinearity. The fluorophore in the GFP has some electronic structure that can be broadly represented in this way. There's an electronic ground state, excited state. There are a lot of vibrational states along the way. And we excite them two-photon resonant in the sense that we're using light that it takes two photons to go near resonant here, although we're not resonant with any of these levels. And then in the first set of experiments, there are parametric processes that can be degenerate or can be non-degenerate in the sense that this photon is, let's say, shifted up, so it has a virtual level lower than this, and then the other photon is shifted down. And of course, then there are non-parametric processes. For example, you could see fluorescence incoherent light that's emitted by this decay from this electronic state to the ground state. So the first task was to go ahead and measure these things, and we create a sample and make these so-called Z-scan measurements that allow us to directly probe this nonlinearity that these fluorophores present. And written here are parameters of our experiment. We're using 200 femtosecond pulses. 785 nanometers take two photons to go above that first electronic level. Power levels, peak intensities, and our solution is either a 1 millimeter or a few millimeter long cuvettes. This EGFP and phosphate buffered solution at concentrations on the order of 20, 25, 30 micromolar. So with these parameters, we can do Z-scan measurements, open aperture that tell us what the two-photon absorption is at those wavelengths, and closed aperture, which tell us what the real part of the nonlinearity associated with that two-photon absorption is. And so here are the measurements. Again, they were presented a while back. We can measure all the parameters. We can measure the saturation. We can measure unsaturated two-photon absorption coefficient, and so data and the measurements match fairly well. You can see that there is saturation as the intensity increases. So at this intensity level, 60 gigawatt per centimeter square, focused in that cuvette, there's about 10% two-photon absorption at the wavelengths that we've used, and then it goes down. And With the open aperture, with the closed aperture Z-scan, we get the refractive, nonlinear refractive index that this solution provides. And once again, we can actually measure the amount of nonlinearity that's presented to this beam as a function of intensity. Again, it fits the data and the model of Gaussian beam propagation through this system fits very well. Okay, so the next task is, after we've measured this, to try to set up some kind of a four-wave mixing experiment. And the first experiment I want to describe to you is just how the geometry is used. And this is degenerate four-wave mixing in the sense that the pump and the two pump waves in this classical, four directions of mixing are at the same frequencies. So this is 785 nanometers. This is also 785 nanometers. And we probe spatially non-degenerate, but at the same wavelength. So some in the community would call this degenerate four-wave mixing. Again, the parameters are listed here. The repetition rate for our source, this pump source, is 13 kilohertz. And later on, I'll present some data where we increase that so we can enhance the photon counting measurements at a slightly higher rate. And again, it's the GFP is contained in this buffered saline solution. So we pump it, and then a probe beam comes in, and as through the third order nonlinearity, an idler is generated. We measure the energy of these pulses, or the average power, and from that we can do measurements on the GFP. But we also compare with other organic dyes just to make sure that the effect, how do they compare with each other. So we've done comparisons with this DCM dye in two different types of solvents, and these pyromethine 556 and another one of the same kind, which is 546. These dyes differ in the sense as to where the peak absorptions are, so in spectra. And again, the goal was to make sure that we have some baseline samples that are just organic dyes. So here's the four-wave mixing efficiency. It's fairly small at the power levels we have, so like on the order of 1% or so. Again, you see larger effects in the case of DCM, but the GFP is down over here. So shown here is intensity in units of the number of photons that are in that pulse, 200 femtosecond pulse, with the focusing, the power that in the previous was intensity in units of gigawatt per centimeter square. If you convert that into a number of photons coming in, so that's the number of photons per pulse. So this 1% level or even smaller efficiency is good enough, because often the goal is to, in our experiments, would be to see how are these photon pairs created in these directions through spontaneous four-wave mixing, where the photon statistics is described by thermal distribution, correlated thermal distributions. And in many of these experiments, the goal is to create the probability of emission to be fairly small, so that you don't have multiple pairs being generated. And because if that happens, and then the entanglement between the two is degraded. So this kind of a few percent efficiency is usually good enough. So we proceed to make photon pair measurements, and that's done now by using non-degenerate four-wave mixing. And the reason is that as these pump pulses come in with 10 to the 12 photons, and they scatter, the cuvettes and the solution itself is not homogeneous enough. There are a few photons that get scattered off, and you want to make sure that these spontaneously generated photons through this nonlinear interaction in this GFP as they go into the signal idler directions, don't pick up any stray photons that get scattered from various surfaces, in particular from these walls of this cuvette. So we moved to actually non-degenerate full-wave mixing, so we can spectrally select this upshifted and downshifted photons by means of spectral filters. And then, of course, that also changes the phase matching geometry because of the dispersion that's present, but you can get back to phase matching by moving these spots around a little bit so that the K vectors match up. And of course, if I don't inject anything here, just the vacuum modes going in these two directions at these spectral windows, then you expect that the distribution here is a joint thermal state between the signal modes and the idler modes. And that can be described then if the average photon number per pulse of excitation is small enough, then we can get paired photons that can be measured. And we do that by employing the usual photon counting methods. So light from those signal and idler directions are coupled into fibers, and they are measured then with photon counting modules. And then after the detection event, the detection events are turned into pulses, pulse trains. And as I said before, the early experiments were done at 13 kilohertz repetition rate, but to increase the pairs being generated, we increased the rep rate to 40 kilohertz, slightly higher, so that any two events, two pulses, are about 25 microseconds apart. And the resolution time of these detectors is on the order of 35 to 40 nanoseconds. So anytime a detection event occurs, you get a TTL pulse that you can record. And listed here are the various parameters, the coupling efficiency into these photon counting modules, and then the actual quantum efficiency of the detectors themselves. And they have dark counts. Once in a while, nothing is coming in and an event occurs, and we keep track of all those. The dark count rate out of these modules is about 25 counts per second, and we can quantify as to various things. And also, we know that these photon pairs, if they're coming in synchronous with the arrival of the pump pulses. So that means that we can implement some kind of a logic here that reduces actually the dark count rate. So we're not counting the dark counts that the detector may have when we're not supposed to be looking. So that allows us to get rid of these counts. And then we do correlations between the two. So we quantify the correlation by means of this, what we call coincidence to accidental ratio. So you measure on these time windows when the pump pulses are coming and how many coincidences are occurring in those time windows. And you compare that with coincidences that may be occurring in adjacent time windows, which they're not supposed to be correlated. And that tells us what the background photons or other sources, so for example, as I mentioned, Raman scattering or other mechanisms for generating photons that could be coming in those channels would be. So we can do these measurements, and again, there's a little bit of animation here. I don't need that. So you look at off time slots, and that gives us the accidental coincidences, and we quantify that means of this coincidence to accidental ratio. So here are the results. For those different dyes, and you can see that in the case of DCMs, there is no correlation. This coincidence to accidental ratio is just 1. On the other hand, in this pyromethane 556, again, there's no correlation. We do some evidence of this correlation with this other dye, but the result is much more remarkable in EGFP. So this ratio is like 40. I think this pointer is kind of. Let me see if I can use this. My pointer is not showing here. So actually, let me just move over here. So So the result is about 40 as opposed to about 6 in this case. And there are many other mechanisms that scatter light. So shown here are stimulated Raman scattering, spontaneous Raman scattering. There are lots of vibrational modes in these dye molecules. The spontaneous full-wave mixing, which is what we're interested in. So there is fluorescence and there is stimulated emission that also comes into play. We quantify all of these. And it turns out that by introducing polarizers, that is measuring photons that are coincidentally polarized with the pump pulses, helps quite a bit. And in fact, when you do that, this coincidence to accidental ratio in EGFP shoots up to 145. So that means that most of the time you're getting paired photons. Of course, the results also get better for this pyrimethane 546, but not as high. So coincidental to accidental ratio about 15 or so. So this shows that in this EGFP, this solution, as these pump photons are coming in and you set up for this full-wave mixing interaction, in this case non-degenerate because we're looking at frequency offset, you see correlations. That necessarily implies that there are time energy entanglement that exists in this system. But time energy entanglement is very hard to probe. So what instead we do is to convert this time energy entanglement into polarization entanglement. And I will show you how we do that. So that's this step 4 here. So here is, so I'm going to show you how we create a state like this out of this spontaneous full-wave mixing interaction. So in the experiment, we have this pulse coming in, which is split into 2 pulses that become the 2 pump beams, and then there are these other directions which phase match, and then in the signal and idler band at different frequency offsets where we do coincidence counting, and those are the results I've shown you. And as I said, by selectively exciting with a polarized pump light helps to improve coincidence to accidental ratio. So then what we do is now to create 2 time slots. You have a pump coming in, it's split into 2 polarization components, so horizontally polarized and vertically polarized. And the horizontally polarized component comes first, preceded by a vertically polarized component that's delayed by a picosecond or a few picoseconds. These are, again, 200 femtosecond type pulses. And then we split them up. So you have a input light which is horizontally polarized, again, creating time epoch on which we have this signal idler pairs being generated, and slightly a few picosecond further behind is the other polarization component that also creates probability amplitudes for these signal idler photon pairs being generated. After that, after the filtering that selects out these the right frequency bands, we go into an output stage which undoes this delay that was put in. And then we do the same on the other path. So again, we have think of it as a Michelson interferometer that's included, and we can put an arbitrary phase delay between the horizontal and the vertical component. And then at the output, that phase delay can be taken out. So now the coincidence slots are overlapping. And then you ask if the pump power here is low enough that only one detection event occurs on the signal channel and one detection event occurs on in the idler channel, then there is polarization entanglement. And here's the evidence for that. So this is now measurements looking at the single counts on each of those detectors. This is data taken over 240 seconds and about 10,000 to 20,000 counts. And then you have coincidence counts in the same time interval. And as you change the relative angle between the analysis directions, so we have polarization halfway plates introduced before the photon counting, and similarly in the other. And of course, you have to fix the polarization. That is, this phase is also important. One can change this phase and relatively change the state that's generated, or you can fix that and create a state and then change that. So in any case, you can see evidence of polarization entanglement that's created. And of course, you can go ahead and do tomography on this. So here we're measuring the density of this polarization density of operator that's created. In the experiment, the target state was this HH plus VV. That was this particular target state. And we measure after doing this polarization tomography as to what state we got. And the state we measure has a fidelity to this of about 94%. This is the reconstructed state. And then we estimate that there is some other amplitude in these other off-diagonal components. So the state actually fits, the measured state fits this kind of a density operator. And the question is, this is slightly different, and why is that the case? And we investigate that. And it turns out that, now let's think in terms of what's happening. So the spontaneous four-way mixing that occurs, the horizontally polarized pump comes first, the way our system is set up. So that means that once that pump pulse comes in, this pair of pulses, in these particular directions, they are setting up the scattering amplitude through this 4-photon scattering process that leads to some kind of a superposition between this electronic ground state and the excited state. And let's call this, and again, this is an ensemble. The state is in this ensemble. And this is so the molecule, the fluorophores and these GFPs that are in this interaction path, they go into this superposition of this excited state and the remaining ground state. Remember, the excitation is fairly weak. So only a 1% chance of this scattering being occurring. And sometime later, you come with this the vertically polarized pulse, and now there's another so some more of this population from the ground state occurs over here. So now you create a superposition of excited states that are horizontal and vertical. And dynamics in these vibronic states has been measured in GFP. So in this paper, the coherent dynamics lasts for about a picosecond or a few picoseconds. So that then shows that there is coherence that exists between these superposed levels at time t equal to 0 and a slightly time later, so long as this time later is not too far away. And in fact, in that case, if this time is very, very short, we should get the exact state. But in our experiment, the time is not really that short. And it so happens that our horizontally polarized pump pulse comes first. And that sort of explains why we get a state like this. As opposed to if, for example, we increase the delay. And now, again, these are the experiments we have not done yet, but this is kind of an explanation for why we have a measured state is slightly different than what we set out to make the target state. And of course, if this time delay is too far, then there should be an incoherent mixture of the HH plus VV. And of course, if they were exactly the same state, one can, depending on that initial phase that I mentioned between the two incident pumps, horizontal, vertical phase, one could create any particular state in principle. And of course, if we flip it, vertical comes first and horizontal comes, then again, we have not tested this yet. We should get a state like this. So, so I guess this kind of, I'm going to wrap up that we have created. So the point here I want to make is that what we are showing is that these fluorophores in these encapsulated GFP proteins in this buffered solution, in some ensemble sense, create entanglement between the light they scatter. But that scattered light also tells us that for the duration of this few hundred femtoseconds up to maybe a picosecond, what is the actual quantum state inside these GFP molecules and this an ensemble of those. And what can we draw from this from the in terms of if we make measurements on this spontaneously scattered photon pairs, quantify the entanglement as that we've done, what does it tell us about the entanglement that exists in this ensemble sense in these GFP fluorophores? That's a question that still remains to be studied and answered. And I want to wrap up by saying that I don't see any difference if this GFP was expressed in a live cell. And in the same way that Vlatko previously was describing his experiments, I don't see why this entanglement would disappear if the cell was alive. Just in the same way that this paper that I mentioned, people have taken GFP expressed in live cells and put them in small cavities and excited them optically and see lasing radiation coming out while the cell is alive. So it's not in vivo, it's kind of ex vivo in some way. So I don't see any reason that we wouldn't be able to study properties of these fluorescent proteins as they are expressed in some live organisms. What does that tell us in terms of quantum state in this biological system that these GFPs are expressed in? That's an open question, and I think that was sort of along the same lines of the discussion we had earlier today. So I think I want to stop here. I want to thank Senwar Shi, whose PhD dissertation was this work that I just presented here, and a whole number of people who contributed to this work.
Are there some questions?
I'd like to explore the relevance of your experiments to living systems a little bit more, and maybe also think about the context of the question for earlier talks. So if you did similar experiments on small organic molecules in polymer films, solid polymer films, would you learn anything different? Would the physics, would the optics be any different? Is there anything special about biology that you're probing?
Right, so that's a very good question. In fact, that's sort of the motivation for us, because we've done spontaneous fluid mixing in fibers, in semiconductors, in various other systems, and we generate entanglement. So the question here was, as I said, my motivation when I started this was I want to be able to create a quantum heuristic in these GFP proteins. And the next step for me would be, can I do mutagenesis, or can I do change some property of these proteins while tagging or selectively picking on a quantum feature?
Does that mean you want to change the characteristics of the chromophore by making modifications to the protein? Yeah, and if so, would that not be any different from changing the polymer medium of surrounding a
But
small
I would be
molecule
genetically
chromophore?
engineering this.
Okay.
I'll be bringing the methods of biology
Gotcha.
to
Chromophore
train,
design.
to create a quantum nest that's better for some purpose. That was the motivation.
Thanks.
Other questions?
My name is Sujata Imani. I actually work for Roger Chen, so that was where my PhD was. So did dimerize GFPs or dimerize fluorophores have different behaviors? Are you planning to investigate that?
I'm not a biologist by training, so as I said.
No, I'm just wondering because you said the chromophore is protected, right, in the beta barrel. So is the quantum behavior as a result of the protection of the chromophore, or could there be, some interactions happening in your ensembles?
So I think having them protected helps. As I said, we tried to create similar kind of correlations in other dye systems. Except for one of the 4 cases we tried, there was small effect. EGFP showed the largest effect possible. So I think there is something to be said about the fact that the fluorophore is protected and this is in a solution, so it never comes together to quench, for example, or reabsorb, or things like that are helpful. Again, that's an initial explanation. I know even if we increase the concentration, and people have done that, if you increase the concentration of these GFPs, then there are quenching effects that start coming in. Our experiments are far away from that. So.
I might have missed it, but what temperature were you doing the experiments at?
Oh, this is all at room temperature.
Okay, have you looked at the influence of temperature then? Because that would kind of probe how much the entanglement is robust to thermal fluctuations.
We have not explored that, but I don't see thermal fluctuations, because this is all optical, right? So
but if the protein is vibrating more and you put more energy into the protein barrel, then will that break the entanglement?
Yeah, that's a good point, and we have not investigated that. Yeah.
Maybe I can ask one question as well. So it's very interesting that you saw a bigger effect in the GFP than in isolated organic molecules. I think a really good control experiment. So in the GFP, you can't take out the chromophore because it requires the protein to fluoresce. But there are other biological molecules where there's a cofactor that you could use for generating entangled light, where you could take that cofactor out and look at it in some kind of solvent versus the protein to perhaps isolate the effect of the protein on this process. Have you considered that?
That would be very interesting, and I'd like to if you can point me in some direction so we can read up a little bit on that. That'd be wonderful. We early on, when we tried to measure this nonlinearity in GFP, we ran a number of control experiments to make sure that the effect thermal nonlinearities, for example, are a lot of artifacts that show up, and we made sure that these nonlinearities, these effects are real. And that we had to control the rep rate to be in the appropriate region, so the heating effects and other things. But I'd like to know more about these control experiments.
Sure.
Thank you.
Sounds good. Any other questions? Okay. So